Hello everyone. Good afternoon students. How are you? I hope everyone is fine. Today, we will begin with our next topic. That is columns with axial force and bending moment. At the end of this lecture, students should 1. Be able to explain the failure modes of compression member, Euler buckling theory, column slenderness and effective buckling length. CO1-PO2. Be able to analyze and design concentrically loaded column CO2-PO5. Be able to discuss the differences between simple and continuous construction CO1-PO2. 4. Be able to analyze and design columns subjected to combined axial and bending for both uniaxial and biaxial bending cases, checking for both cross-sections and buckling resistances CO2-PO5. Here are the course outcomes and program outcomes for this subject. Compression members are the most common of structural elements carrying either axial load, with or without bending moment. The picture shows several examples of compression members. The top left figure shows a compression member in a structural frame building, almost known as column, while the top right figure shows some part of the compression member in roof truss. And the third figure, which is at the bottom, shows a bridge structure, in which some part of the members are in compression. In this topic, we will learn on how to design a compression members. The focus will be on column design. Columns or compression members are the most common of structural elements carrying either axial load, with or without bending moment. In this topic, we will learn on how to design axially loaded column and column carrying axial load and bending moment. Okay, let's first start with axially loaded column, or some people will address it as concentrically loaded column. Axially loaded column. Axially loaded column is a column which only carrying axial forces. However, it is very unusual cases, column will be carrying axial loaded alone. As you can see here, most of the column will be subjected to either singly or doubly moment together with axial load. For example, a corner column highlighted in yellow box, assuming the load carrying by beam 1 and beam B are equal, thus being cancelled out. Thus in this case, the column C will be subjected to axial forces from the upper column C, and bending moment from the secondary beam, as shown in the figure. Basically, compression members subjected to an axial load are susceptible to squashing in a short column. However, squashing only occurs in short column, in which the slenderness ratio is lesser than 0.2. Apart from that, other failure modes are overall flexural buckling, torsional buckling, local buckling. Local buckling can be controlled by section classification. As you can see in ECS571, Table 5.2, with the least section being Class 3, in which, for an internal compression part, the ratio of outstand web, C, over the thickness of web, TW, is less than or equal to 42 strain. And for an internal compression part, the ratio of outstand flange, C, over the thickness of flange, TF, is less than or equal to 14 strain. The design requirements for compression members are given in EC3-1-1, Clause 6.2.4. The design overall buckling resistance of a column is given in Clause 6.3.1.1.3, EC3-1-1 as given in A circumflex for Class 1 to Class 3, and B for Class 4, where the reduction factor for the relevant buckling mode determined from Clause 6.3.1.2, EC3-1-1. Euler buckling is an elastic buckling developed by a mathematician Leonhard Euler in 1757. It derives a formula that gives the maximum axial load that a long, slender and ideal column can carry without buckling. An ideal column is one that is perfectly straight, homogeneous and free from initial stress. The formula derived by Euler for ideal columns is shown here. However, a real column has geometrical imperfection and presence of residual stresses. Residual stress is the stresses developed in steel section during production, whereby geometrical imperfection usually causes the column to have initial out of straightness after rolling. Residual stresses in structural members can play an important role in buckling. Residual stresses result from all types of manufacturing and fabrication processes used in practice, for instance, hot rolling process. Here is the example of hot rolling process. Such stresses are formed due to the non-uniform temperature distribution during cooling after the rolling process. During the cooling process, the area which are the most exposed to the air will first dry.
Rolls until the final thickness and shape are achieved. To do this, the rolls must exert forces of tens of millions of newtons, equivalent to a weight of thousands of tons. The rolls, therefore, run in massive bearings, mounted in housings of enormous strength and driven by powerful electric motors. These are known as mill stands. The layout of a rolling mill can vary from a simple single-stand mill to several stands positioned either side by side or in a line. The mill rolls themselves can either be plain for flat products such as strip, used for products such as cladding, or profiled for sections, beams and columns for use in construction. Mill stands have various roll arrangements depending on the product being rolled. The simplest arrangement is a two-high stand, used mainly for long products such as sections. For light sections and bars, three-high stands are sometimes used, with the steel passing one way through the bottom gap and back through the top gap. Four-high stands have two work rolls in contact with the steel, supported by larger backup rolls to prevent distortion caused by the rolling face. These give greater accuracy for rolling flat products, such as plate. Universal beam mills include stands with both horizontal and vertical rolls bearing on the steel simultaneously. Rolling processes are computer-controlled and monitored up to 50 times per second. Despite the huge scale of some mills, accuracy to plus or minus 50 microns can be measured. The rolled steel is then cooled in a way appropriate to its end use and prepared for further processing or dispatch.
In this case, during the cooling process, the area which are the most exposed to the air will first cold. These areas are the one highlighted in the red box. All the tip flanges and the middle part of the web will first cold, in which causes the compression between all the molecules at this area, and at the same time pulling the molecules in the area highlighted in the blue box. The compression and tension stress occur during the cooling process after the hot rolling mill are called residual stresses. In a real column, buckling occurs when the column non-dimensional slenderness is high. Clause 6.3.1.3 EC3-1-1 defines the slenderness ratio. As you can see, for class 1 to class 3, the slenderness ratio is given in A, while for class 4, the slenderness ratio is given in B. Slenderness of columns, commonly encountered in building construction, is low, and these columns are considered as stocky members and will buckle inelastically. It is highlighted that, for A, members resisting loads other than wind loads, non-dimensional slenderness is equals 180. B, members resisting self-weight and wind loads, non-dimensional slenderness is equals 250. C. Tension tie subjected to load reversal by wind, non-dimensional slenderness is equals 350. EC3 provides little information on how to determine critical buckling length. Different end restraints affect the buckling lengths of the column. This experiment shows the effect of different end restraint to the buckling length of a column.
The specimen is a rectangular hollow section made from structural steel. The length has been chosen so that the failure is dominated by buckling instability. This is primarily a geometric effect. The loading diagram shows a compressive force evenly applied to both ends of the specimen. The testing rig is now starting to apply a compressive force to the specimen. We can see the top end displacing and the column begins to deflect sideways as a result of a structural instability, which is better known as buckling. The profile of the column as it buckles is theoretically a full cosine wave. Note that the column ends do not rotate due to the fixed-ended conditions. The column maintains this shape as it continues to deflect, until eventually material damage takes hold, which distorts the shape. This particular phenomenon is dominated by the elastic behavior, and material effects are secondary but ultimately trigger failure. This video shows a pin-ended column of low slenderness being tested in compression. This type of specimen is commonly referred to as a stocky column. The specimen is a rectangular hollow section made of structural steel. The length has been chosen such that the failure is dominated by the material strength. The loading diagram shows a purely axial compressive force evenly applied to both ends of the specimen. The testing rig is now starting to apply a compressive force to the specimen. We can see the top end displacing and the column begins to deflect sideways as a result of the material damage, which can be seen at midspan on the concave side. Once this occurs, the column begins to lose its load carrying capacity. This particular phenomenon is not in the elastic but in the plastic range. Therefore, the failure is governed by the material rather than the geometry of the specimen. Turning the specimen to the side, you can see that the deformation has localized to the midspan of the specimen in a plastic hinge.
EC3 provides little information on how to determine critical buckling length. Different end restraints affect the buckling lengths of the column. The end restraints could be refer to table of buckling length, extracts from EC3, page 7. This figure shows different types of end restraints together with their critical buckling length formula for non-sway mode structure. And this figure shows different types of end restraints together with their critical buckling length formula for sway mode structure. There are 4 major design processes in designing compression members. The first is strength classification, which you can refer to table 3.1. EC3-1-1. Second is the section classification, which you can refer to table 5.2, EC3-1-1. Third is the compression resistance of cross-section, which you can refer to clause 6.2.4, EC3-1-1. And the last step is to check buckling resistance of compression member, given in clause 6.3.1.1, EC3-1-1. Okay, students, let's proceed with our first example. That is design of axially loaded column. See you in the next video.